Right, okay, thanks everyone for coming along to .NET Chef this evening. Pleasure to be here. Last time I did .NET Chef was, Bonfire Night 2019, Kev, configuration. So let's go with it then. Get my clicker ready. Is the clicker working? Yeah. So first things first, quick introduction from me before we get going. My name's Steve Collins. I've been programming in one form or another since the early 80s, but professionally I've been doing this since the early 90s, starting with VB3 right the way through to now using .NET 5. As I've got quite a common name, I go by the alias of Steve Talks Code for both my blog, Twitter handle, and anywhere else you can find me. I've got a lot to pack in, but as there isn't another speaker, normally I have to do this talk in an hour and I sort of go at a rate of knots. So I'm going to slow it down tonight. I've got breaks about every 20 minutes or so, where if you've got some questions, we'll have a catch up on questions at that point. I'm just going to put in chat. There's a whole load of links throughout the talk, but I've done a gist on GitHub. So if you want to find any of the links I go to, just go to that gist and all the links are there. So with the introductions out the way, let's go deep into dependency injection. So before we get going, as this is quite a deep dive into the more advanced topics of dependency injection in .NET Core and .NET 5, I've made quite a few assumptions about what you probably already know about using DI. First is most of you familiar with using a host builder of one flavor or another to go and create your container. Whilst you can also create the container directly from the service collection without a host builder, I'm not going to go into that much in this talk. Next assumption is that you're familiar with using a startup class to register your services, and you do that through a configure services method. Then you get the host builder to use your startup class via the use startup method, and it's using sort of a generic reference to it. So as you can see here, we're using a default host builder to set up the web application, and we're using the more specific web host builder because this is an ASP.NET Core application. Next, there's various types of dependency injection supported by many of the IOC containers. But for now, you just need to be aware that out the box, the .NET Core container only supports constructor injection. Now, when I say .NET Core, as I kind of alluded to in the titles, I'm also covering .NET 5, and I have got some specifics about .NET 5 and C#9 later on in the chat. If you're using ASP.NET Core, you do get to take advantage of one other type of injection out of the box, and that's method parameter injection. So as you can see here on the slide, all you need to do is use the from services attribute on your parameters that you want injected into from the container into your controller actions, rather than having go through your constructor. This means that if you've got lots of actions on your controller that have different dependencies, you can avoid having to throw them all into the constructor. So every time something comes in, all these dependencies come in, even if your particular action only needs one or two of them. By doing this, it makes your controllers and your action methods much more aligned with the single responsibility principle from Solid. Now, usually, if you want to go beyond the basic out-the-box experience of the Microsoft container, you usually have to go and look at one of the other containers that are out there. But before I cover that, let's look at the other injection types that aren't supported out the box. Firstly, we've got property injection. This is where you've got some kind of class, usually not one of your own, that has a parameters constructor, and you have to go and set it all up by setting properties. And then once you've got that all set up, you usually call something like initialize or build or create or something like that. Those aren't handled by, because it's a parameterless constructor, the DI container can't handle that. So you have to look at other ways of dealing with that. But some of the other IOC containers can deal with it. Next, we've got named or key-based injection. This is where you identify the dependency by using some type of key, typically string, enum, or a constant. Lastly, it's not an injection type per se, but you've got automatic service registration by convention, which is a long-winded way of sort of saying that the container that you use in scans assemblies and pulls out classes and interfaces to register based on a set of conventions or rules that you specify. Good news is that hopefully over the next hour or so, I'll be showing you some workarounds so that you can implement these just using the out-the-box container without necessarily having to go off to use one of the other containers. But why are those other styles of injection not really supported? Well, the Microsoft container is what's known as a conforming container. This is a term coined by Mark Seaman, who is sort of Mr. Dependency Injection, to describe a container that acts as an abstraction over other containers. The problem with this is that only the lowest common denominator of functionality is supported. So whilst the Microsoft container is a container that can stand alone, because it allows other containers to hook into a common interface, it's fairly basic in what it can do out of the box. So you're probably aware that there's a number of other container frameworks out there that can be used with .NET. So in this slide, I show the ones that are listed on the Microsoft Docs website as having been adapted or extended to work with the iService provider interface. Now, the downside is if you want to use functionality that's not directly supported by the Microsoft container, you have to manage your interactions with both containers side by side. This means you need to know how and who is resolving your dependencies for you. But before we look at those other containers, let's look at how you set up the out-the-box container. So in this snippet, we have code that you're likely to be familiar with. Here, we're just registering some classes with the service collection and giving them different lifetimes, just inside the startup class. Now, as we've already covered, in most applications, you'll be using a host builder that initializes the service collection with some default services. Once it's done that, it will create an instance of your startup class and then call the configure services method. And it goes and adds the registrations you've specified as shown here. After that, it will then call the build service provider method on the service collection to go and create the container instance based on these service registrations. Once built, the container can be used by the application to resolve instances of services whenever they're required. Now, if you're familiar with .NET Core 2, you'll have been used to building that container at the end of your configure services method and returning it as an iService provider instance. And that was the way you were able to wire up your alternative containers. So as an example, here I'm using AutoFac to register an AutoFac module and return a new AutoFac container in .NET Core 2. But all this changed with .NET Core 3. So we went from the very specific web host builder to a generic host builder. And that expects to be taken care of calling the build service provider itself. So if you've got a method that tries to return the service provider from configure services in Core 3 or .NET 5, you'll actually get a Roslyn Analyzer warning. Reason for this is that the provider instance that you create is not used by the host builder because it expects to go and build it itself. So you've incurred the expense of going and building a provider that's just going to get thrown away. What it also means that whilst in Core 2, there was a small performance boost by implementing the iStartup interface when using the web host builder, that's no longer true because the generic model doesn't really use it. If you can't create the service provider in your startup class, though, how do you wire up your alternative providers? Because we saw in .NET Core 2, that's how you did it. To do it in Core 3 onwards, there's now a use service provider factory extension method that you add to the host builder. To get that, and what that does is that gets you your alternative container that resolves the instances for you via the Microsoft abstraction. Whilst that will register the custom container, you still need to perform any container-specific configuration in the configure container method. So this is where you do any fancy stuff in AutoFac to do with, say, key dependencies, for example. You can do this with the configure container extension method on the host builder, but to be honest, it's a bit of a pain. So it's a lot easier to actually do it in your startup class as shown here. So where I've got AutoFac, whichever way you choose to do it, you need to set the parameter to receive the builder instance that is specific to that third-party container you're using so that that container's own registration methods can be used. So for example, here, we've got AutoFac, which will provide a container builder instance, which is AutoFac's builder technology, where you can register AutoFac modules, for example. Important to note, though, as the container is built by the host builder, you can't access the created container until you get to the configure method, where you can access it via the application services property. So having covered how the container gets built, let's give some consideration to the lifetimes of the object instances you want the container to create for you. Now, I'm sure this is familiar territory, but I've included it to make sure everyone's up to the same level of understanding before we delve any deeper. So firstly, you've got singletons, which are created only once and live for the duration of your application. Next, we've got transients, who are sort of kind of our fair weather friends and come and go as and when needed on demand. And last but not least, we have scope lifetimes, which kind of stand between the other two, but I'll cover those in a little bit later. The thing to consider with these different lifetimes is that some play well with each other and others should be kept apart. They're not good friends. So let's break it down. Starting with the shortest lived of the lifetimes, the transient can accept objects created by any of the three lifetimes. Moving up, we next have scope lifetimes, which, because it's slightly longer lived than the transient, it shouldn't really have a transient lifetime object injected into it. Lastly, we have the singleton. And as this is the longest lived of all, this should only have other singletons injected into it and not the other two. Now, I've tried to choose my words carefully when describing these relationships because there's a general misconception that it's not possible to inject incompatible lifetimes into each other. But that's not strictly true. Can't speak for other containers, but the Microsoft container won't actually stop you. If you have a singleton and its constructor requires an instance of something that in your configured services has been registered as a transient or scoped, the container will happily give you that instance. Problem is, the instance you'll get will have its lifetime promoted up to being that it's the same as the receiving instance. So in this case, your transient or scoped will in effect become singletons. In other words, what happens is you get your transient trapped. And then what happens is it doesn't get released until your singleton gets disposed of and it's done dusted. This is known as a capture dependency, where the transient or scoped instance, like the insect in amber shown here, is imprisoned in an outer shell, which in our case is the singleton. But you may be wanting to sort of, hey, hang on, when I've done this before, I've got an exception. Yep, that can occur. By default, it only happens when your ASP.NET Core environment variable is set to development. This is done by some hidden magic that lies in the host builder. However, you can explicitly turn this behavior on by setting up the optional validate scopes parameter to true when you create the service provider. This does have a bit of a performance hit on your startup though. So the general guidance from Microsoft is don't do it in production. Now, while I'm not really going to cover it here today, there's also a validate on build method. And what that will do is try and help identify if you've got an incoming dependency to one of your registered services and you haven't registered that other dependency. So if you've got a class A that has a dependency on class B and you haven't registered class B, it will try and identify you for you. It's fairly limited in the amount of things it'll do. So I wouldn't necessarily rely on it as a fail safe for you, but it is quite useful to do while you're sort of initially doing your development. So moving on, given that singletons live a long lifetime, and they can be dangerous when mixing with other lifetimes, let's consider why we use singletons in the typical use cases. Given singletons can be accessed anywhere within the application, things get tricky if your application uses multiple threads. Therefore, singletons should ideally be stateless so you avoid threading complications. But sometimes you may well have some sort of state that you need to share. These might be pooled resources, in-memory queues, or some other types that are in control of a limited resource that multiple things are dependent upon. Factory classes I'll talk about later, but typically, once these are created, you use their methods to go and create other short-lived instances of other things that you have a dependency upon. You may have an ambient singleton, which hides the complexity of accessing shorter-lived objects, something like the HTTP context accessor in ASP.NET Core. And that uses async local storage to do some sort of nasty trickery behind the scenes, using threads and synchronizing context behind the scenes. The last of the cases shown here is a mutable state, where you don't want to have to recreate the resource object over and over and over again, when you know that the data that inside it doesn't really change while your application's running. So for example, you might have some lookup data that you read once from a slow repository, such as a database, a file, or a network service. If you really must have state, give some thought to letting .NET do some of the heavy lifting for you. If you have collections, consider the concurrent collections namespace where the thread safety stuff has been done for you already. For read-only properties that have an underlying field, make the field read-only so that if someone comes along later and tries to make the property read-write, you put some guardrails in place that make them think, oh, that's read-only, therefore I've got to actually do something. Do I really want to do this? Is that what was in the original design? For those properties that need to be read-write, you have to resort to using the thread lock. Now, this is contentious, but bear with me. So in this thread, we can see that we're ensuring all property access is managed by the thread lock. That way, we can ensure that the value is only changed by only one thread at a time. Now, you're probably 2 steps ahead of me, but the problem with this approach is that by serializing access to the property, you'll get a major performance hit as you're forcing everything down a sort of one at a time alleyway to get to that particular property or resource. You can then end up with threads queuing, or even worse, if it gets itself in a bit of a twist, you could end up with thread deadlocks. So you probably need to consider whether your design is actually correct if you're having to do that. And you may want to reconsider, is singleton the actual best way to do it? Could you be using something like async local? Don't have a panacea for this, just sort of waving my flag that it's a bit of a code smell and you might want to address it, especially if you're doing a web application. Less so in a console app, but still not great. Lastly, we'll want to consider the impact of having disposables in a singleton. So whilst it's not a threading race condition, like the ones I've just previously described, the problem here is that if you expose the dispose method and a consumer calls it, everyone else has potentially lost access to the disposed resources, which can in turn cause a object disposed exception to be raised elsewhere in the application where you're least expecting it. However, you do still need to make sure that the dispose method itself is still there for the container to clean up after itself once it's done with the disposable resource. To get around this, you may want to consider abstracting the class with an interface that exposes all the members of your class except the dispose method. That way, given that the service type is an interface and not the concrete class that you're registering, when the instance is served up from the container, you've put some guardrails in place that make it difficult for the consumer to accidentally call dispose on the instance, as it's not on the interface. Now, of course, that doesn't stop someone from casting that instance back into the concrete type if it's public, and then calling dispose. But to be honest, it's their foot, and if they want to shoot themselves in it, that's up to them. Next, at the other end of the lifetime scale, we have transients. Now, for these, there's not really a lot to say, other than be careful about doing a lot of work in the constructor, as you don't really have control over when these instances are created by the container, because they could be called from all over the place. This could have a major performance effect on your application if they're doing something like getting data from a database and spinning up connections, spinning up calls to web services, things like that. So what you're better off doing is, rather than doing that in constructor, is having a very explicit method on those particular classes to go and do that work, so that the caller knows it's going off to do something, rather than being hidden during the construction by the container. Moving on to scope lifetimes, these need to be approached with caution and handled with care. In fact, I've seen various blog posts and tweets where people have said, I'm not having those on my project, they're dangerous, no way. A little bit drastic, but I totally understand the reticence, as they can come back and bite you really hard when you least expect it if used incorrectly. So hopefully I can clear up some of the pain points. Now, we've already covered how scoped instances should be used by other lifetimes. But what exactly is a scoped instance? The commonly quoted answer is that they're created by ASP.NET Core for an HTTP request response lifetime. But that's not the whole story. Whilst there is a common use case, whilst it is a common use case, a scope is not directly tied to ASP.NET. You can go and create your own scopes, but it still doesn't answer what a scope actually is. So to my thinking, the scope is really there to ensure that objects are created only once within a single unit of work. So say you have several classes that are all considered to be within a single unit of work. Those classes interact with each other and all depend on receiving, say, an iWidget instance in their constructor when created by the container. Therefore, you want to make sure that all of those instances still get that one instance of iWidget. So in that respect, a scope lifetime is a bit like a singleton in that you get to share a particular instance amongst multiple classes derived from the container. However, outside that work boundary, you expect to get a different instance. So in that way, it's a bit like a transient. Each time you've got a new unit of work, you get a new instance of your scoped lifetime instance. So going back to our web example with ASP.NET, if Kev and I both make a web request and those request response pipelines are individual units of work, therefore a scoped instance should be confined to each pipe's boundary. If you think about it, what Kev maybe puts in his web request is of no interest to my web request. However, as I talked about earlier, it is possible to accidentally promote a scope dependency up to a singleton if it's injected into a singleton constructor and it becomes the capture dependency. Away from the web, you might be writing, say, a Xamarin or a console application, and you may want to manually create a scope yourself to, again, create your single unit of work. This is done by calling the create scope method on the iService provider interface. This gives you back an iService scope with a single property of service provider, which in turn gives you an iService provider. It all gets a bit Inception. But this time you've created a boundary around your scope services. So it's all a bit hard to sort of explain verbally. So let's look at a diagram. At the top, we have what's known as the root provider. And this is where you usually get the singletons and transients generated. The create scope method on that wraps a lot of what I've just tried to explain by creating your scope provider for you. And that's where you get your scope services from. Now in ASP.NET Core, the creation of the scopes is taken care of for you when the request response lifetime is started. What happens behind the scenes is that the server will create a whole load of what are known as service features, but the one we're interested in is the request service feature. As I described just now, the scope factory is used to create the scope as highlighted here, and then the scope that is used is then, the scope is then used to create the scope service provider, which is then accessed from the HTTP context request services property. That's all great, but as someone who's just writing ASP.NET controllers, this is all pretty much hidden away from you, and you don't really care. All you care about is making sure that your constructor or action method, if you're using the from services attribute, get the services they want from the container. However, there is one area of ASP.NET Core where it is worth knowing what's going on under the hood, and that's middleware. Now, when we talk about middleware, we think about intercepting and handling HTTP requests and responses. Now, because you think what we've just been talking about, scopes and HTTP requests, you might assume that middleware is a scoped registration, but that's not strictly true, because there's two ways of writing middleware. The one that most people are familiar with, because it's been around since .NET Core 1, is convention-based middleware. Now, with this type of middleware, you accept a request delegate in the constructor and then call it from within the invoke async method. And then you move to the next middleware in the pipeline via async, invoke async, and so on, so on, so on, goes down. Now, inside your middleware, if you want to actually do something, you usually do it either before or after the delegate call to the next link in the chain. In some cases, you might be writing terminating middleware, where you generate a response and you don't go on to that next delegate, for example, unless you can't handle the request. That's how something like static file middleware works. If you have dependencies other than the HTTP context, you add those as parameters to the invoke async method, and they magically appear when the method gets called by the pipeline. But how does that happen? When you register middleware, it's done in the configure method of the startup class. At this point, the container is already baked, so you're not actually adding your middleware to the container. Instead, what's going on is that you're inserting a delegate into the invoke async method that will be doing the actual work in the pipeline. To do that, it has to go and create an single instance of the middleware class that is created using the use middleware method. When that single instance is created, any dependencies are resolved from the root container. Now, as we saw earlier, if the constructor is only called once, when you inject a transient or a scope dependency into that Singleton constructor, even though we're not using the container, it becomes a captured dependency. What you also need to bear in mind is that the pipeline is created before the first request is received. So with that in mind, you won't actually be able to access the HTTP context in the constructor, as at that point, you're building the pipeline before the first request is coming. The HTTP context just doesn't exist at that point. And what happens is you get an invalid operation exception thrown, as it can't resolve the HTTP context because it doesn't exist at the point you're creating the pipeline. Now, other scope dependencies that aren't part of the pipeline may well resolve, but as I say, they become captured dependencies. So how does the request, which by nature is scoped, get dealt with? Oops, sorry, jumping ahead of myself. Well, as the request moves through each layer of the middleware in the pipeline, the invoke async method gets called through the delegate chain, not through some interface or abstract contract. To do this, when the middleware is added to the pipeline, a request delegate is created. The delegate acts as a wrapper over the invoke async method. As you can see, the request delegate is passed as a parameter in the middleware constructor to enable the request to be passed down to the next one in the pipeline. So you cache it in a field and then call it in the invoke async. Now you're free to add any scoped or transient dependencies as parameters to the invoke async method if you need them in order to do some work, either before or after the next middleware in the pipeline. In the previous example, I demonstrated how dependency injection works with convention-based middleware. Now, the problem with convention-based middleware is that it feels a bit clunky, and certainly when I've written it, there's a few bear traps, especially to do with transients and scope lifetimes, if you've not got your wits about you on it. What's less well known, and I only found out about it a few months ago, is that there was an interface introduced with ASP.NET Core 2 called iMiddleware. Now, what iMiddleware interface allows you to do is turn what we just described in convention-based middleware completely on its head. This time, the invoke async method is a fixed signature. You don't add your dependencies into that, it's fixed. And that's part of the iMiddleware interface. So whilst we still get the HTTP context passed into it, the request delegate is now passed in via the method and not the constructor. So given that the method has a fixed signature, we have to go back to the constructor to be able to inject our dependencies. But what's different this time is that instead of some hidden magic using reflection going on under the bonnet in the pipeline, the middleware instance is now constructed by the DI container. So unlike convention-based middleware, we do need to remember to register our middleware with the configure services. Oops. Now, when we call the use middleware method to register the middleware, the method checks to see if our middleware type implements our middleware interface. If it does, then it will go and get the middleware instance from the container. If it doesn't, then it'll assume it's convention-based middleware and then work as it did before. Now, what happens inside that creation of going to the container is it goes via an iMiddleware factory that's registered in the DI container. It doesn't go direct to the container. Now that feels like an unnecessary step. The container knows how to do it. Why don't I just go to the container? But the reason behind that is going back to the start of the talk, is you can register other IOC containers. So if you went straight to the container, you'd be going through the iService provider. It's only the stuff that the conventional based way of registering services by the Microsoft container can get called. If you want to do any of the funky stuff that, say, AutoFac does, then it bypasses that. So by using the iMiddleware factory, it allows those other containers, such as AutoFac, to go and produce an instance of one of those for you. So if, for example, you've got an AutoFac registration, that knows how to do things like going and using key registered instances, for example. Those implementations, going down this route, writing middleware becomes much more natural as you write it in the same way as you write other .NET classes that you would register with the DI container, because it becomes very much like a normal POCO, for example, that does some work. Now, if you're interested in finding out more about the conventional versus factory-based middleware and how they work with dependency injection, I do have a blog post that goes into more detail and does a detailed comparison about how convention-based middleware works, how factory-based middleware works, and how they work with the underlying use method in the application builder class, which is the thing that actually does the building of the pipeline. So having covered the different lifetimes, I think that's a good place to stop and answer some questions. So I'm just having a quick look. No, nothing in chat. Does anyone want to raise any questions coming off mute? No? Okay, I'll have a quick sip of drink. I'll carry on. So earlier, I mentioned that you need to be careful with disposables, but now I want to dig a bit deeper into some edge cases. If you remember, when I was talking about singletons, I said that you should hide the dispose method from consumers as the container will take care of it. Last bit of that statement is true in most cases, but as you can see here in this bit page I grabbed from the Microsoft Docs website, there are a couple of the extension methods where you can go and create the instance yourself and the container won't dispose of those for you. Now, if you do create an instance of a disposable class in this way, there's a problem. Namely, that there's no obvious re-entry point back into configure services method or the startup class to get a reference to that instance to then go and dispose it. So why would you take that approach? Most likely reason is that you need to pass some arguments into the constructor that cannot be created by the container. If that is the case, you should maybe consider using a factory. But if you really, really must do this, there is a get out of jail card. Behind the scenes, there's an interface that it gets automatically registered by the host called iHost application lifetime. This can be injected into the configure method by adding it to the method's parameter list. Inside the method, you can register a handler for the application shutdown event, which is past the object that you want to dispose of. That's fine if you've just got one object that you've done like that. It gets really, really messy if you've got lots of them. Rather than setting up all this plumbing, my advice would be to wrap the object creation up inside your own disposable class. So say you've got 5 different things of these disposable things. Is go and create your own class that implements iDisposable. Go and new them up inside your class, and then go and dispose of them inside your class. So your class is the only thing that has to be disposed of. If you've got no parameters coming into your class, you can register that in the usual way, and the container will then go and dispose of it as per normal. Now, I've started writing a blog post on that, and I'm hoping to publish that in the next couple of weeks to explain the differences between what I've just shown there and how you can work around it. Now, that approach doesn't just apply to that example. Coming back to hiding the dispose method, if you can't change the disposable class because you don't own the source code and it doesn't already have an abstraction that hides the dispose method, you may want to consider one of the gang of 4 patterns such as facade, adapter, bridge, or proxy. These are all variations of the same kind of theme in that what you're doing is you're creating a wrapper class to handle the creation and disposal of the class instance. Now, the last point I want to make on this slide is a rare one. and it's very definitely a code smell. Sometimes you might have a class that you inject these disposable things into, and rather than you disposing it from the outside, it wants to dispose of them from inside. And that's known as a control freak, and basically it's an anti-pattern. So just be aware that if you're expecting something that you're expecting you're going to dispose something, and something goes and disposes of it for you unwittingly, because you've gone through your container with it, you might start getting the object disposed exceptions coming up all over the place. So if you get in other classes, just be wary of them if they might do that. Hopefully that shouldn't happen, but it could. So next we've got some gotchas that can come up and bite you when registering or consuming services from the container. Consider what happens when the same service type gets registered multiple times against multiple implementations. Now, you may be deliberately doing that, and I'll come on to that in a minute, but it can happen by accident. So, for example, you may have got a source code merge that's gone wrong. So you've got something that used to register class A. You've done a code merge that now registers class B, but the code merge has gone wrong, so you're registering both A and B. Or you may have an extension method registering different implementations to the one you're registering without you know about it. You've brought some NuGet package in. You don't necessarily know what it's doing behind the scenes. Whatever the reason, there can be unintended consequences because of the way the container works. And that's namely the last in wins principle. So if you call an extension method after your registration, it'll be the implementation that the extension method has registered that gets resolved by the container, not necessarily yours. Similarly, you might have an extension method that get you doing configure services, and then you register something afterwards. So yours kicks in, and it might be that there's some dependency somewhere down the line that expects the one that the extension method registered. So you do need to give some thoughts into the order that you set up your dependencies and configure services. Now, of course, if you're writing an extension method, the onus is on you to play nicely, especially if you're publishing it via NuGet for the public consumption. As we know, there needs to be care around lifetimes, and things get really messy if you've got multiple registrations of the same service type and they've all got different lifetimes. So you may think you've registered a singleton, and then something else unbeknownst to you comes along and trumps it with a transient or singleton scoped. Now, it may be that, as I mentioned just now, that's happened by accident, but you may deliberately want to be doing it. But if you want to avoid the accidental registration of the same service having multiple times, there are two ways out the box that you can do this. The first is to, instead of just using add singleton, add transient, add scope, it's to use the triad versions of those methods. What that does is it flips from a last in wins principle to a first in wins principle, because the triad, a bit like when you've got triad in a dictionary, we'll say, if it already exists, I'm not going to add it again. The second approach is to use the triad enumerable methods. Now, triads will only look at the service registration, whereas triad enumerable will look at both the service registration and the implementation. So in the examples I've got shown here, we've got the triad singleton, which will result in just one registration, even though it's been called 6 times. But the triad enumerable will result in 3 registrations, because this time it will take the implementation into account as well. So that's the gotchas done. Let's look at some helpful hints and tricks. Flipping what I've just talked about on its head, and I alluded to it as I started, you may be deliberately registering multiple implementations that the caller needs to iterate over. Now, a typical example of this may be something like you're building up collections of things, or you might have some kind of enrichment process, which uses the visitor pattern that sort of says, I want to do this process A, then I want to take what process A is generated and move it into process B, into process C, and so on, so on, so on. And you could use the enumerable registrations to say, effectively, a bit like we talked about with middleware, to build up this pipeline of work where you iterate through all the different processes. If you plan to do this, the consuming class needs to know that there are going to be multiple registrations. Now, as is done explicitly in the consuming class, typically maybe your can't think of the word controller, and it sort of says, I know I need to do this pipeline of work, so I'm going to ask for an IEnumerable of these processes, and I will iterate through them to do what I need to do. If you do register multiple things and you don't do this, you're back to either the last in wins principle, if you just use add, or the first in wins principle if you use the triad methods. What is also important to consider is that because it's an enumerable, the order of registration determines the order that the consuming enumerable is received. So without, what you need to then think of is, does the order of registration matter to the consumer? Now, there's lots of ways of handling this. One way is to create a comparer that implements iComparable interface on your service type, and then the consumer can do an order by link, so that you're putting the onus on the consumer. You could create a dedicated class that implements the IEnumerable interface, and the caller requests that. So instead of getting the order of registration, you've explicitly registered IEnumerable, and you have a class that says, I'm going to yield this up in a particular order. Lastly, you could just register a Lambda expression for IEnumerable in the container, and then do something inside there, which is using, say, a switch statement or something like that. But that feels a bit clunky. My preference is to actually have a dedicated class if you want to control the ordering. Going the other way round, you may have a single class that has multiple interfaces, especially if you've gone down the interface segregation principle route from solid. Now, if you register the type with each interface individually, so you sort of say, I'm just looking up on my slide, interface 1 of X, interface 2 of X, interface 3 of X. If you call on those, each will get a new instance. When really what you probably want is the same instance returned, especially if it's a singleton or scoped. If you want to access the same instance through different interface, what you should do is register the instance first by its class type, and then use Lambda expressions using the getRequiredService method to resolve the main instance from the container and return it via the appropriate interface. Now, in some cases, you may want to aggregate the interfaces together into a composite interface as shown here. This may be a benefit if you don't want consumers to be able to request concrete implementation directly. So if you think back to earlier, I was saying about hiding the concrete implementation if you don't want to expose the dispose method. So you abstract it away. So what you could do is aggregate all your interfaces together and then say that your class is going to implement that aggregate interface. Next, we have open generics, where you define a type parameter on the class type. Now, the place you may be familiar with this most in DI perspective is from the iLoggerT interface, where you may be using it to get your controller constructors to get an instance of the logger, and you're using the generic to sort of say, I want to register, when it logs stuff, I want it to say that it's coming from my controller. Similarly, you may be familiar with the iOptions interface that gets registered when you use the configure method to bind configuration object to objects. If you want to register your own generic type, the C# syntax doesn't really lend itself to referencing open generics from within a generic declaration. So instead, what you have to use the non-generic registration method, where we use the type of keyword to get the service and implementation types without giving the closing type parameter. In the case shown here, the iDoSomething generic interface and the doSomething generic interface, generic class, sorry, are shown with the angle brackets, but without the closing type parameter, as this will be supplied by the consumer. Behind the scenes, the container makes use of the makeGenericType method on the type class to create a closed generic type. So for example, do something generic of strings. Now, you wouldn't really do that with strings because strings is sort of a rubbish example, but you get where I'm trying to come from. It then uses that type with a bit of reflection magic to go and create the closed generic instance to return to the caller. Now, if you haven't moved to .NET 5 yet, you will hit a problem if your type definition includes a constraint on the generic type, such as limiting it to being a class or limiting it to being a particular interface. The problem is that the make generic type was throwing an argument exception. However, that's where Jimmy Bogard of Automapper mediator fame has come to the rescue. Now, he did a pull request that added a try catch around the make generic type that swallows the argument exception. This now allows the constrained generics to be resolved in .NET 5, which is great, except it took 4 years for Microsoft to accept his pull request. Now, if you read Jimmy's blog, you get to understand why there's been very little change in the Microsoft container since the first version of .NET Core. In short, you have to ensure that all the other container technologies that implement iService Provider that we talked about at the beginning, that you're not going to break them. It's not just about the Microsoft container, which in turn means you have to write a whole load of unit tests and not only show that what you're changing fixes something or adds something of value to all the containers, it also shows that you haven't broken anything. Next, I want to talk about a couple of the so-called Gang of Four design patterns that are really relevant when you're in the working with a DI container. The first is the factory pattern, which I've mentioned in passing throughout the talk. Now, you may be thinking, hang on, surely the whole point of the container is to be a factory of instances for me. Why do I need to go and write a factory? Sometimes you need to give the DI container a helping hand because it can't necessarily do all the work that you need it to do for you. So, for example, you may have a class where some of the constructor parameters aren't known until runtime because they might be captured from user input, say in a web application. So the container's not going to know how to spin those up. In those cases, you can't get the container to create that instance. So what do? You could do some hideous hack with async local, but that's all pretty nasty stuff. So you may have a situation where you've got an instance that needs to be disposed of quickly because it's an absolute resource hog and you don't want the containers to do that. Sorry, I've lost my plan. Lastly, at the start of the talk, I mentioned that the Microsoft container doesn't support property injection. But by using the factory, we can effectively simulate property injection by getting the container to instantiate the class and then set the property values by returning a fully prepared instance. So those are just a few instances of where the factory pattern comes into its own. So it's a very quick and very contrived example. We have a class that will register as a singleton. Next, we're going to go and create a class that consumes that singleton, but also requires a name parameter in the constructor. Now, given that the name parameter can't be known by the container, as it's provided at runtime by our API controller, we can't just go and add it to the configure services. Now, what you may notice here is I've used an immutable class here, but with C#9, I could have used a record type instead. Now we go and create a factory class. First, we'll go and take the singleton and cache it in a field, as shown in the blue highlighted constructor. We then have a creation method, which will go and new up our short-lived thing class using the cache singleton and passing in the value from our name parameter that we've got on our factory method. Next, we add the factory to the configure services as a singleton. And finally, we have our controller that takes our factory and its constructor. Later in the get action, it then calls the make method, or we could have called it build, or we could have called it create, to return a new instance of the short-lived thing. Very contrived, I know, but it gives a flavor of where you could use a factory. I apologize for the sort of small font I've had to use on that if you're watching on a small screen, but I had to pack a lot into that slide. So to summarize factories, usually you'll register a factory as a singleton, as most of the time it's stateless. The variations are the parameters used in the create method as it's called. As it is a singleton, the only other dependencies that should be injected into it are other singletons. If you need transients or scope dependencies, you could take the iService provider itself as a constructor parameter, but proceed with caution. Direct use of the iService provider is considered a version of what's known as the service locator anti-pattern. The reason it's an anti-pattern is that it's tightly coupling your classes to the container interfaces, which in most cases you don't want to do. You want your classes, especially if they're domain classes that might be shared around, to be oblivious to the container technology, because someone might want to use them with, say, AutoFac in Framework if you're doing, say, a .NET Standard project, for example. However, the factory pattern classes fall into a group that I refer to as servicing classes, as these are plugging the gaps in the container functionality and are effectively an extension to the container. So with that in mind, I think as long as the factory classes are seen in that context, and you keep them maybe within the same project where you've got your startup class, you're not and you don't go referencing iService provider whole scale throughout your application. I'm fairly relaxed about that, and it's being pragmatic rather than dogmatic. But certainly if you're doing classes in libraries to be consumed by other people, I wouldn't necessarily go down that route. If you are worried about factory classes exposing that anti-pattern, what you could do is go and create an interface that makes the class private inside your startup class. That way, the container can go and construct them, but callers can only access the methods of the registered interface. That way, the exposure of iService provider is limited to just your startup class. A variation of the factory pattern is the builder pattern, where rather than prescribing which dependencies are needed up front and then just go and creating the instance just like that, the builder is much more flexible. The way I compare the two patterns is to think of them as like the drinks dispensers in, say, a fast food restaurant. The factory is like asking a person serving for a cola from a standardized dispenser, and it's got a fixed set of options of diet cola, full sugar cola, etc. The builder pattern is much more like the dispenser on the right, which you see in sort of like the modern chains, where you can sort of say, okay, I've got a base cola, but then I want to add a dash of lime and maybe some vanilla and some cherry flavoring, gradually composing the customized version up until you've got the finished drink that you want. So with the builder, we start out very much like the factory by registering the container. However, this time, whereas the factory is a singleton, this time we're going to register it as a transient, because once it's created and you consume it, you're going to be mutating the state of it to go and get your eventual class that you want it to build. Consuming classes take the builder as a constructor parameter and then start using methods and properties to build up the new instance to be constructed. So to use the drink example, say you've got something that builds a drink, it will start with a base cola that it might have injected from the container, but then it's up to you to say, add lime, add vanilla, add cherry, and so on. Basically building up your instance until it's what you want, and then calling the build method. Once you've got that, depending on what you want to do with it, most of the time you'll probably want to make it immutable. The last thing I want to mention is that, like factory, if the instance you create by the builder is disposable, it's the caller's responsibility to call the dispose method on it, because the containers had no part in the construction of it. It's only responsible for the builder itself, not the things that the builder builds, if that makes sense. Now, so far, we've assumed that the factory or builder classes will be using the new keyword to instantiate the class instance. But wouldn't it be good if we could take advantage of the container to create the instance for us? In earlier slides, I said the problem with that was working out how to populate the parameters that the container doesn't know about. Luckily, that's where the activated utilities class comes in handy. Now, there's 4 methods. There are effectively 2 methods with generic overloads. The get service or create service will try and get the container to create an instance of something for you. If the type isn't registered, it'll just do it via reflection, sort of activate or create. The other method, and the one that's of interest to us as factory or builder class creators, is the create instance method. What this does is it takes an instance of iService provider to get an inroad to the container, and then it takes an array of objects. What it then does, it does the hard work of trying to match up the constructor signatures of what you're asking for against the array of objects you've got, and tries matching them all up. Now, the downside to that is you're going to take a bit of a performance hit because you're getting activated utilities to do some try and work it out for you. Whereas if you've only got maybe 2 or 3 parameters, you might be better off just newing it up yourself because you know the signature of what you want. But it can be a useful thing to have in your back pocket if you may want to have something that's got different signatures and different parameters that you want to do the marrying up for you instead of you having to do lots of switch statements, for example. Phew. So quick breath. Any questions? Or no? Okay. Anyone want to come off mute, ask questions before I carry on?
Just that the factory stuff. It's quite common for people to inject in like a funk of tea.
Bear with me, Kevin. bear with me. That's coming up.
Okay, I'll be quiet.
Anyone else? No? Okay, I'll carry on. So in this final section, I want to talk about plugging in some of the gaps in functionality that the Microsoft container is missing. Now, I mentioned earlier that property injection is supported out of the box by the Microsoft container. And as we've shown, you can get around that with a factory or builder pattern to go and sort of set stuff up for you and then just call create or build as appropriate. Another place where that's useful is if you need to create instances of struct value types, where some of the properties might be coming from the container. Now, the problem here is that you simply cannot register value types, so struct types, with the Microsoft DI container. It's not supported. It only supports reference types. So you need to get all the dependencies and instantiate the value type yourself. Easily, I'm attempting to add a struct type registration with the generic add transient, and here's the Roslyn analyzer error to say it's a no can do. Aha! Could be because I'm using generic registration. I'll try the non-generic version. And that's great. You don't get a compile time error. All you've done is you've kicked the problem down the road to runtime instead. So how do we get around this? We can simply create a factory or builder that takes parameters needed to populate the values, the value types that we don't already have from the container. Now, the example here, contrived yet again, and offers no benefit of just newing up the objects yourself. However, if some of the properties need to be taken from the container, this is where the factory can grab them in the constructor via the IO service provider and put them together with the methods. So it might be useful if you've got, say, Singleton. So instead of, and it might be if you've got something that's buried way down in the hierarchy, you don't want to have to grab all these things that say your controller and then have to pass them all the way down. What'd be nice is if you can say those things, the builder or factory knows how to get them. I need to just worry about the things it doesn't know about. So we've talked about value types as structs, but that leads us nicely onto C#9 record types. Big fan of these and make heavy use of them at the moment. For those not familiar with them, they're reference types, so basically classes, but they behave like value types when it comes to things like equality checking. They also offer a simplified syntax for immutability. Now, they're not necessarily immutable by default, but there are certain ways of registering them, creating them, do make them immutable. If you want to find out more, I like the on.net show video there's a link to here. From a DI perspective, as they're reference types, you can register them with a container because right down deep at IL level, they're basically classes. However, given that record types are mainly used for entities, you're more likely to use the factory pattern for the same reasons as I gave in the previous few slides about structs. But if you are interested in finding out more about using records as factories, I do have a blog post that I show here. Next, we have something no one really talks about with dependency injection. And this is kind of what Kev's just alluded to. We nearly always talk about using classes and interfaces being registered with a container, but delegates are also a first-class citizen that can also be registered. Now, in theory, you can register the anonymous delegates from the funct family, but these are hard to distinguish from each other as they're generic. So instead, we can go old school back to something that doesn't get much attention these days, and that's using custom delegates. Now, I'll go into details on my blog, but I'll give you a quick example. I really hate system date time now being littered through my code base. The date is non-deterministic, it's hard to unit test and so on. But what we can do is create a delegate function that will call the system date time now property on our behalf. Now, the signature of the delegate in this case is a function with no input parameters and a return type of date time. By creating the delegate, we are creating an abstraction without all the ceremony of having to first create the interface, then go and create an implementing class that then wraps that dreadful static property. This makes your registration code much cleaner, as you don't need to go through all that plumbing. It also feeds into the single responsibility principles. The delegate just does just one thing. If you want multiple datetime related features, you could go and create an interface and class. But if those functions don't share any logic, you could just go create multiple delegates. Now, this is where the custom delegates have the advantage over the funct family, as the delegates all have the same signature, but distinguished by a delegate name. And under the bonnet, what it's really doing is creating anonymous classes for you. If you do try and do this with the funct family, they may all have the same function signature, and therefore you do risk running into the trap of the multiple registrations that I talked about earlier. From a unit testing point of view, the delegates are very easy to mock and create your own implementations, as they are just in effect functions that return the date time. So as long as you can write a function that has the same signature, you can use it in your unit tests and then test it with your assert statements. Now, you may notice that I've registered the delegate as a singleton, maybe thinking that the datetime return will be captured as the first time it's called. But that's not the case, as what we're capturing is the delegate reference, not the delegate's results. So you don't actually get those results until you invoke it from the caller. This is the same principle that's what's being used when you build your middleware pipeline. So in yet another contrived example, I consume the delegate in the controller constructor and cache it in a field. I then invoke it at the time the constructor is run and cache it in a field then. In the get action, I force a 3-second delay, and then I call the delegate again. And then I go and create a return string with both values. And as you can see here, the result shows that even though the delegate is a singleton, the result is not generated until it's invoked in the two different places I've invoked it, the first in the constructor and the second in the get. And therefore, you get the 3-second difference as shown in the result. A feature that's supported by other containers, such as AutoFac, is being able to specify a dependency to be resolved in the container by using a string name or a key. It's considered a little bit of an anti-pattern, as it comes back to the idea that your application code should not know about the container's mechanics. But what if you could do it without your class having to know, clicker's gone a bit mad. What if you could do it without your class having knowledge of the container in use? So this occurred to me a while back when I had a situation where the type of mapping algorithm to use was determined at runtime based on a value I was retrieving from the database. So rather than writing a massive hard-coded switch statement inside my repository class, I wanted to be able to have it so that I just got the value from the database and said, I want the container to go and get the thing that I need to do with it. So the mapping functionality in this case. It's a bit long-winded to describe here, and I do have a link to my blog post. But to give you an idea of what's involved, I have an example where we create a common interface and some classes. So here we have a temperature converters that go from different scales into kelvins. We then register them all with the container as their actual types. Now, following on from what I was saying about using delegates, we also have a delegate declared that takes a string and returns the required implementation of the iKelvin mapper interface. Now, in the code here, I've used a simple switch statement based on character values, just for simplicity within this example. But I could have done something more advanced with using dictionaries or custom attributes or on the implementing types, or maybe pattern matching. Whichever way you choose to do it, the delegate is the secret sauce in that it allows us to lift the logic out of the consumer and up into the container. The consumer will use the delegate to pass in the string key and get back the correct mapper instance that it wants. In other words, we have something along the lines of an abstract factory pattern. So now we have a consumer class called getTemperatures that has a method to take a scale as a string and a decimal value and it uses the delegate to convert that into the kelvins. Our class has no knowledge of the container's service provider or how the required implementations get chosen from the string. It just knows that if I get a string that says C, it wants a converter to go from centigrade to kelvins. So that was somewhat contrived and simplified example of using inline switch statements. Now, after I wrote my blog, Frank Quedno has written a blog post that uses it as a sort of starting point. And he goes off and looks at things like using dictionaries and who points out some gotchas around closures using the service provider. So that's well worth a look as well. Decorator is another gang of four pattern that can be used to extend the functionality of a class by wrapping it and then re-implementing all the members. But where necessary, it goes and intercepts the incoming parameters and all the outgoing results to do something else. Now, the most common example you're probably familiar with is to add some logging. So every call to a method's input gets logged and the results coming on the output also get logged. To do this, we still need the original class to be injected into the decorating class along with our other dependencies, which in our case is a logger. So in the example code here, we have a class called doSomething that implements the IDoSomething interface. First, we register the class as a concrete type and not through its interface. We then have a decorating class called loggingDoSomething that takes the registered original class and also requires an instance of iLogger. It then re-implements the getHello message method. This time, it intercepts the input and the output of doSomething's version and writes out to a log file. We then go back and register the new loggingDoSomething against the IDoSomething interface, which is used by the consumers. Now, the last missing feature from the Microsoft container that is supported by some other containers is the register of services by convention or assembly scanning. Personally, I'm not a big fan of doing this as I'm a bit of a control freak and I like to know exactly what's going on with my registrations, especially as I said about the gotchas earlier about lifetimes and things stamping over each other. However, if you have masses of classes that need registering, this can be a laborious process, and I totally understand why you're probably looking for a shortcut. There's several offerings out there, but probably the most well-known is Scruta, where you can define a set of rules or criteria for registering classes and interfaces by pointing at an assembly. One nice thing I do like about Scruta, even though I don't particularly not a big fan of auto registration, is the stuff I've just been talking about using Decorator. It has various extension methods that take a lot of that plumbing away from you. And you can just sort of say, I want to decorate this class with this other class instead. Much simpler syntax than using the hand crank version I showed just now. One last topic I want to give a brief mention to is about performance. Now, some of your registered classes might take a while to get instantiated when you first new up the object. And this is where I was saying about the dangers of your transients doing things like database calls, but you might be doing something in, say, a Singleton where you take one hit on reading a data file that you want to then expose as sort of read-only data. If this is the case, you may want to consider using some kind of background hosted service that starts up the application, with the application, and then requests all the Singleton services before your first request comes in. Now, this has two benefits. Namely, Singletons get instantiated and are ready to go when that first request comes in. But you could also do it with some transients and scopes, because whilst you'll be throwing them away, not using them again, it does have the benefit of kicking in the JIT compilation for those. So whilst there's not a benefit of newing them up for the sake of newing them up, once it's gone through that JIT compilation, that it doesn't need to do that JIT again for it. It already knows the compiled object. Andrew Locke's got a really good blog post on this, and I highly recommend reading it. Oh, that just about wraps it up. Thank you for coming tonight. I hope I haven't sort of just gone blah and then thrown tons and tons and tons of information at you. Hopefully there's a few things to take away that will be of use. If you want to hear any more of my ramblings, I'm on Twitter quite a bit. I have a blog that I've been shamelessly self-promoting throughout this talk, mainly talking about dependency injection. And originally I started about configuration, but Kev has taken over as the king of configuration on talks now. Few honorable mentions: Andrew Locke, brilliant blog that covers all sorts of things about .NET Core related. And he's just in fact, he's just published the second edition of ASP.NET Core in Action, which is available from the Manning website. Microsoft Docs pages are well worth a look, especially if you've migrated from Core 2 to Core 3 or now .NET 5. And last but no means least, Mark Seaman's blog and book are well worth looking at, especially if you want to get the bigger picture about DI patterns and anti-patterns. And with that said, I've just about got enough voice and breath to say thank you for coming. That's it.